So we are live. Hello everyone, welcome to the day 6 of ML Maths Clubs by TFUG Ghaziabad. We will be starting with our expert speaker that we have here within our studio. So we will just wait for 1 or 2 minutes to let our participants join. After that, we can start the stream. Until then, you can drop your hi hellos in the comment. We will be starting at 7:02. Okay, so let's start with the session. Hello, everyone. My name is Madhur Agarwal. I'm a core team member from TFUG Ghaziabad. We are here with the day 6 of ML Math Club's 8 episode campaign from TFUG Ghaziabad. Today, we have Saurav Prateek in our studio, our expert speaker, who is a web solutions engineer too at Google, ex Geeks for Geeks. So let's welcome Saurav with drop your comments in the YouTube stream. Welcome, Saurav, and thank you for being here today. He'll be talking about linear regression in machine learning. He's a profound speaker, expert, and he has been mentoring students for quite some time. He also have a YouTube channel for which I will drop the link in the YouTube description itself. You can check out there. Okay, Mike is yours, Saurav.
Hey, thanks, Madhur, for the introduction. Hey, hello, everyone. My name is Saurav Prateek. I'm a web solutions engineer here at Google, and I'm working with Google from past 3 years. And yeah, in this episode, we'll be talking about linear regression. So we'll mostly be walking through the mathematics, and at the end, we'll also spend some time in building up a real-time linear regression model on an example data set, and we'll see how to compute the scores and how to test your model, right? So we'll do all of that. Uh, okay. Cool. So this is my introduction, already given, so I'll just skip this slide. So let's talk about the agenda of this session first. So what we have in plan is that we'll start with the introduction of linear regression. Then we will discuss about the hypothesis. We'll be covering some maths under it. We'll discuss the cost function. So basically how to define or how to evaluate whether your model is good enough or not, right? We'll also discuss gradient descent, like how gradient descent helps in providing the minimum value for your cost functions. After that, we'll discuss about evaluation matrix. What are the rest of the evaluation matrix that are used widely in linear regression, right, to assess the model? Then we'll also talk about some of the assumptions and considerations in linear regression, right? And after that, we'll discuss about overfitting and underfitting, like one of the two major topics in machine learning. And at the end, we'll discuss degrees of freedom. That's a very underrated topic. I might not discussed a lot in linear regression sessions, but we're gonna discuss that. We're gonna cover that in depth as well. And once all of these are done, we're gonna walk through the code snippet, trying to implement a linear regression model. The practicals will be done in Kaggle. So we have I have a Kaggle notebook in place. I'm gonna we'll hop over to that Kaggle notebook and see how does that go. Okay. Cool. And feel free to ask your questions in the comment sections. I can see that. So I'll try to respond as much as I can. And if not, we'll definitely take up at the end of this session. Okay, cool. So starting with the introduction, what a linear regression model looks like. So it is one of the most simplest model when we talk about machine learning, right? So what we do is that we try to perform a best fit. So first of all, linear regression is a supervised learning model. Basically, we have already have that training data set with us on the basis of which we try to build up a model, and then we use that model to test on the testing data sets. So that is the concept here. So again, linear regression is a supervised learning model. The second thing to note about is that it always works on a continuous data set, or when your data set is a continuous numbers, right? It does not work on categorical data sets. So these are the two things to note first when we are starting with linear regression, right? The second thing is that what we do in a linear regression is that we have some independent variables, right? So there are some independent variables. On the basis of that, we try to decide how the dependent variable will behave. These independent variables can be features in the data set, right? So suppose you have a data set, there are some of the features, right? So those features can be called independent variables. Why it is called independent variable? Because they are not dependent on anything. They can independently change within the data set. That is why these are called independent variables. And on the basis of these independent variables, our final result, that is the variable y, changes. And that is why it is called a dependent variable. And what we try to do is that we try to perform a best fit, like try to understand how our dependent variable changes when our independent variable uh, deviates or changes its behavior. So here you'll see the best fit line, which is in the um, left of the graph here, right? This is a very basic linear regression model which I have shown. We'll talk more in the next slides. So coming to the next slide, what a best fit line is. So you'll see again, we'll talk about the output and the predictor variables. So here the predictor variable are the independent variables, right? So independent variable goes into the x-axis and the dependent variable is at the y-axis. So as the independent variable changes, the dependent variable also changes. And that is what captured by a linear regression best fit line. So here you'll see that in the left of the diagram, the independent variable x increases, the dependent variable also increases. So when x is increasing, the y is also increasing, and that is what the line is trying to show. For lower values of x, there is a lower value of y. For as the value of x increases, the value of y also increases. And that is, this can be called a best fit line. So what is a best fit line? So basically, if you have all your data sets in place, then best fit line can be a line which gives you a minimal error. And what do we mean by a minimal error? So by minimal error, we means that there is a minimum deviation between what is the observed value and what is the predicted value. So if that difference in those values are minimal and that is being shown by a line, then we can say that that is a best fit line, right? And what is these errors called? So these errors are also called residuals. So residuals are nothing but what the difference between the observed and the predicted value. So if at a particular value, at a particular point X, your model is predicting a value Y and its actual value was something else, then the difference between those two values will give you an error. And in the linear regression, the best fit line tries to minimize that error so that your model can predict the dependent variable on the basis of those independent variable. That is the concept. That is the entire like thing which linear regression model tries to capture. Okay, cool. Let's move ahead. So we'll talk about hypothesis now. So here we are looking in more in detail how a linear regression model looks like. So this is a very basic linear regression model where we have only one independent variable, that is x. And the hypothesis function looks like this, where y is equal to theta1 plus theta2 x, where theta1 and theta2 are the parameters. So it is very similar to this curve or line equation which we have read in maths, right? Where y is equal to mx plus c, where m is a slope and c is the intercept. Similarly, here y is theta 2x plus theta 1, where theta 2 is the slope and theta 1 is the intercept. And that is what we are trying to show here in this um, graph. Another interesting thing this graph shows is you will see at point xi, the value of y is pi. So this is actually the predicted value because this best fit line is predicting at xi, the value of y should be pi. But you will also see that there is a data set, which is the actual data set present, which is yi. at xi as well. This is the actual value, and the difference that is between yi and ti is called the error. So that is the error in your linear regression model, that the actual value was here and the predicted value is here, and this line between them is the difference between the yi and the actual value and the predicted value, and that's what we are trying to minimize by through linear regression. That's what the model tries to do. So we try to minimize this, and that is the concept behind the linear regression model. So this is the line looks like y is equal to theta 1 plus theta 2x. It's very similar to y equal to mx plus c, the equation for a straight line, right? So hope this looks good. Okay, cool. Let's move on to the next slide. Okay, so talking about the cost function. So in the previous slide, we saw this graph, right? Now we'll talk about the cost function. So cost function is nothing but the difference between the actual value and the predicted value. So what we try to do is that we always try to minimize the cost function, right? So by minimizing the cost function, we mean that we try to make sure that our predicted value is very, very much in line with the actual values. And that's how our model will improve, right? So if you'll see this minimum square error, that MSE is nothing but the difference between this actual value, yi, minus the predicted value. And the predicted value is nothing but it is b naught plus bixi. This is what our y value, y predicted value was. So we are just replacing the y predicted value with the actual theta 1 plus theta 2 x here in order to get the full equation. So that is, this is the maths behind this. So if you'll see what the entire mean squared error looks like, this is yi minus y naught the square, and y naught is can be said as the predicted value, which has been replaced by the actual linear regression or the line equation. And we are trying to square it because we don't want to uh, differentiate between the positive and the negative error differences. We don't want them to cancel out each other. That is why we are making sure even if this error is negative, it adds up to the mean squared error. And that is why we are trying to make a square of it. And then since this term is mean squared error, there is a word mean in it, and mean is nothing but average. And that is why we are dividing it by the sample size. So that's the whole equation. So yi minus predicted y whole square divided by n, where predicted y is being replaced by the actual value. This is the cost function. And what we try to do in linear regression, we try to minimize this cost function so that our model performs the best. And how we minimize this cost function? We use a gradient descent method. So gradient descent method we'll talk about in the further slides. So we use gradient descent method to minimize this minimum square error. And how to minimize, what does gradient descent method do? So gradient descent method tries to come up with a suitable values of b naught and b1 so that our minimum mean squared error is minimized. That is the concept here. So we have to like the gradient descent method comes up with a value of b naught and b1 so that we try to minimize the mean squared error, right? So that is the concept here with the cost function. Now in the slides ahead, what we'll try to do is that we'll try to understand the gradient descent method and what it tries to do actually. So if any question, like feel free to put that in the comments. Be happy to take up. Otherwise, we'll move on to the next slide. Okay, so talking about the gradient descent in linear regression. So gradient descent is one of the optimization functions or optimization algorithms that optimizes the cost function. So cost function was nothing. This was the cost function which we are talking about. Cost function, you see, this is a squared function, right? So the curve will not be linear. If you plot this cost function on a xy axis, it will never be a linear curve. It will always be a curved curve. It will not be a straight line, and that's what we are plotting here. It's a curve. So we are trying to plot the uh, mean mean squared error or the cost function here. And what gradient descent method tries to do? Gradient descent method tries to come up with the values of b naught and b1 so that we can get the minimum value here. Now, if you'll see in the graph here, you can see that the minimum value is at the bottom which is also pointed as the optimal value, and that's what we are shooting for. We have to from any place in the curve, we have to reach to the optimal value, and at this place, whatever the value of b0 and b1 is, should be uh, placed in the model and will be considered as the effective values, so that the cost function can be reduced, right? And the question is that how gradient descent does that, like how gradient descent comes up with values of b0 and b1, so that this entire cost function can be minimized, right? That is the question we are trying to answer. So you must have heard about learning rates. Okay. Do we have a question by Vedansh? Hey, sir, can you please tell me how to minimize cost function, affect values, and learning in neural networks? Yeah. So I'll not talk about neural networks here, but I'll definitely talk about how to minimize the cost function. That's what we are moving ahead with. So how to minimize the cost function? So you must have heard about the term learning rate, right? So we need in the while you are tuning your model, you have to specify your learning rate. It is the rate at which how fast your model adapts, right? Now, what gradient descent method does, if we move ahead in the graph, what it tries to do is that it puts initially you at some place in this curve, and you might be at the at the initial or at the upper point of this curve, and it tries to move ahead. So it tries to decide whether I have to step left or do I have to step right, how to decide which direction to move. So, and also how to decide how much to move. So, how to decide how much to move, that is called the learning rate. So, if I decide my learning rate to be, say, 3 units, then it might be moving 3 steps or 3 units left and 3 units right, and it will decide which direction to move. So, we know how much to move. So, learning rate decides how much to move. Now, in which direction to move, we can easily decide if this is curve like this, which has a global minima at the which has one global minima, then if you will move to the left and the right direction, then one of them will be the lower value. So here, if we move left, we get a higher value, and if we move right, we get a lower value. And in this way, we decide that we have to go into the right direction because the global minima is at the right direction. And that's what we do. So if the learning rate is good enough, you will gonna keep moving right direction, and you will definitely reach to the optimal value. Because how will you know that that is the optimal value? Because when you are at the optimal or at the lowest place, and you will try to move one step ahead, or the step decided by learning rate, right, the learning rate step ahead, you will see that now you're not hitting another minimum value, there is another maximum value. And you'll see that at this point the left is also maximum and the right is also maximum. And then you decide that, okay, left is also maximum, right is maximum, it means that I am at a global minima, and this is an optimal value where I can return the values of b0 and b, right? Okay, so we have a question again here, Saurav. My question is that we use mean squared error. How mean versus median will affect this metric? Uh, I'm not sure, man. Median is a totally different, um, I say, computation. So mean is actually it does the average, and that's why it works. Median is not actually it's not totally the average value, right? Median is something different. It is computed somewhat different, and it will not give you I can definitely tell you that it will not give you a minimum that if you use median in your cost function, although you will be able to go to the minimal value, but that will not give you that will not give you an essence of a minimal function, right? That's not a good cost effective function. That's what we have to choose, a good function, right? That's what we did in the cost function. We went with mean squared error, not a median squared error, because median squared error is not a cost function. It's not a good cost function. Mean squared error is a good cost function. It tries to average out all the samples. That's why we are going with the MSE. That's the whole concept here. The start. Okay, I hope that clarifies. But yeah, so I was talking about the learning rate, right? So learning rate is nothing but how many steps you are trying to move, or gradient descent method is trying to move in left or right direction, and then trying to understand which direction to move ahead, right? Okay. So that is the learning rate. That is by definition that is called the learning rate. Now there are two things which can happen. So you as a author, or you who is training the model, have to provide a learning rate, or you can provide a learning rate. You have the ability to provide a learning rate. Otherwise, model might go with a default learning rate value. but you think that you have a better learning rate in place, you can provide that. Now, in those situations, two things can happen. Either you can like, or three things can happen. You can provide a good learning rate, optimal learning rate, in which your model may reach the optimal value. You can give a very huge learning rate, and in that case, your model may go like crazy. Sometimes you'll get higher value, sometimes get lower value. Or you might give a very small learning rate, and in that case, your model will take a lot of time to reach the global minimum. So these are the three things that can happen when you are deciding a learning rate. Now we'll try to discuss all of these three things in detail. So I hope till this part we are clear. We have discussed the learning rate. We have discussed how gradient descent method uses learning rate to go to the global minima, right? We also discussed the cost functions here, right? And how gradient descent helps in minimizing the cost function. Okay, we'll be moving ahead. So what we are talking about is the overshooting and slow learning rate. So these are the two terms. Overshooting is nothing but when you take the learning rate value to be very high, then what happens is that you overshoot. Overshoot means you miss the global minimum. That's what here happened. We are at this point, and from this, we choose the learning rate to be really high. And that is why we missed the global minima and we went to the other side of the curve. Again, what happened is that we came here and decided, oh, I have skipped the global minima, and we had the algorithm, again, the Gaussian method decided to go to the next direction, but the learning rate was too high. So it was not able to again reach the global minima, it again reached to the left part, and it keeps on jumping to the left side, right side, left side, right side, and it never reaches the global minima. That was the problem with the higher learning rate. You will never reach the global minima. You will keep moving at the extremes of this bell curve, and that should not happen. So that is one of the drawbacks of choosing a higher learning rate. Now, what happens when you do a lower learning rate? So lower learning rate or a smaller learning rate, what happens is that if you give a very small value to the learning rate, your gradient descent method will go into the right direction, will always proceed to the right direction. But what will happen is that it will proceed very slowly. And it at that time, it will take a lot of iteration or a lot of epochs for your machine learning algorithm to reach to the or to come up with the efficient V naught and V1 value. So these are the two things which you need to keep in mind when you are deciding a good learning rate. Like you don't do an overshooting and you don't fall for a very low learning rate. Right. So these are the two concepts which we need to keep in mind. Okay. Okay. A good question by Rashmi Agarwal. Is there any way to plot this kind of curve during the training so that we can understand and analyze the metric? Actually, Rashmi, we don't need to actually plot the curve. So this, when you train the model, it is taken care by the model internally. It builds the cost function. The Gaussian method tries to come up with a better value of B0 and B1. What we have to do is that we need to decide the learning rate and the epoch value. So epoch value is basically how much iteration you want your algorithm to iterate to come up with the efficient B0 and B1 value. So these things are probably taken care by the model. But if you want, you can definitely um, plot the curve, because you will already have your, if you know that what are the, if you have one independent variable, and if you have the equation ready, then you can plot it, but it will take you some time, because that's a pure math we are talking about. You're trying to like do plot a min square error. But again, if you do that, you have to write a Gaussian algorithm on yourself. That is also not very hard to write. Maybe you can do some binary search here, right? It looks like the Gaussian method looks very similar to the binary search, right? You move left, you right, and then you decide where in which direction to go, and then again at that place you move left, right, and decide which direction to go. So you can have a learning rate. You can build a method with we have learning rate, and you can move left, right, and then you can decide which direction to go. So the logic looks clear, I guess. Like if but it is possible to build this on with Scratch, I guess. But I haven't tried it, so I can't comment here. Yeah. How to find the optimal epochs of our model? So we don't know actually. We have to try it out. We have to give different learning rates. We have to give different epochs and try to find which combination should work. A lot of times I have seen multiple people um, giving a list of epochs with a combination of a list of learning rates and comparing the cost function or comparing the testing results of that model, like which one performed the best, and they went ahead with that. right? So I've seen that happened as well. So you have to like play around with with this learning rate and the epochs to decide which one is the best, given you have the training data set in hand. Okay. Okay, moving ahead, evaluation matrix in the linear regression. So the question is, how do you evaluate your model? So first we talked about mean squared error, right? That is one of the very good metric to evaluate your linear regression model. But there are other uh, metric as well, which may be even better than the mean squared error. So these are the two which I'm going to talk about. First is the R squared, or it is also called coefficient of determination. So R squared is a very interesting metric. So as far we have all mostly talked about those metrics which describe error, but this is one metric which describe the deviation which is explained by the model, right? So in most of these like matrix, you try to minimize the value, right? But here in R square, you want that your R square value should be greater or should touch the number one, that is the maximum value, so that your model is effective. And how does it do that? So within that R squared is nothing but the amount of variation which can be captured by your model. And that's what you want. You want your model to capture most of the deviation so that it does not go into the error, right? Most of the deviation, if majority of the deviation is captured by your model, then your model is performing, right? The values of the R squared always range between 0 and 1. The higher the value, the better the model. Now, how mathematically can represent it? So I'll first cover this R square, then I'll come back, I'll cover RMSE, that is the root mean square. So this is complex as well, but very interesting to understand. So how to mathematically represent it? So it is nothing but 1 minus RSS by TSS. Now, what is RSS and TSS? That is an interesting thing to note. So here I have described RSS and TSS. So RSS is residual sum of squares, right? So we discussed residue, right? Residue was nothing but the difference between the predicted value and the actual value, right? It's a square. It's basically the difference between that. And what is this residual sum of square? So we sum up the residual, we sum up the square of the residual, and we get the RSS. That is the equation we have here. Y1 minus prediction of y. Prediction of y was nothing but b naught plus b1x, which if we minus it, all the terms got subtracted. So yi minus b naught minus b1x, the whole square, because it's the sum of squares. Now residual sum of squares, we do it for all the samples, right? We have a actual value and the predicted value by the model. We subtract it and we sum up for all of these. And when we do that, we get an RSS. Now, RSS, looking at this, what do you want your RSS to be? So you want your RSS to be as minimum as possible, because the lesser the RSS value, the lesser the error in your model. So the RSS value should be minimized in order for your model to perform. And that is what the reason is, because that's what is 1 minus RSS by TSS. So lower the value of RSS, the higher the value of your R squared model, or the R2 value, and higher the value of your R squared metric, better the model performance. So it all correlates here. Now, what is TSS? So TSS is the total sum of squares. It is nothing but the difference between the mean value and the actual variable. So you see here yi minus y bar. So bar is nothing but the mean. Mean is you sum up all the samples and you divide it by n, you got the mean. That's what here in the right side, we have tried to describe that in the graph here. So there are a lot of y values, which is shown by the gray dots. And there is a line which represents a y bar. Y bar is nothing, we have sum up all the y samples and divided by n. And that's why this line is at the middle, because we have some dots at the left, some dots at the right, and the mean is at the middle. This is y bar, and TSS is nothing but the difference between y and y bar, that how much deviation of an actual value from the mean value. That's what it. So this green dot and this green line describes your TSS for this particular green dot. That is y minus y bar. We sum up this TSS for all the samples, and we get the actual TSS value. And when we have this RSS and TSS, I hope you understood the RSS and TSS definitions here. Then R square is nothing but 1 minus RSS by TSS. And that's what this R squared value is. So higher the value of R squared, better the model. And that is R squared for us. Now, talking about root mean squared error, that is also called RMSE in short. It is not very complex. It's just RSS by n under root because it's a mean squared. So RSS was basically the difference between the predicted value and the actual values, right? What we did is that it's a mean squared, right? So mean means we have to divide it by n to average out, and it's squared, so we underroot it to get the RMSE value, right? Now RMSE is not similar to R squared. RMSE gives the actual error value, so we want the RMSE value to be as minimum as possible. The lower the value of RMSE, the higher the performance of the model, right? And RSS we discussed earlier in this slide, right? RSS is nothing but y predicted minus actual values of y, the whole square. And that's what we have shown here. We have replaced the RSS with its actual numbers, and we have divided by n, the under root, to get the RMSE value, right? So these are the two evaluation metrics that is very fondly used in linear regression model to decide how your model is performing. And that's what like we talked about here. So these are the evaluation metrics. I think this is like R squared can be complex, but if you clarify RSS and TSS, the definition, if the definition of RSS and TSS is clear in your mind, then you can easily come up with the R squared value, right? Okay, cool. Now we'll look at this. We'll try to understand the R squared method more in more depth, maybe. So this curve shows the significance of R squared metric. As I have like told earlier that higher the value of R square, the better your model performance. So that's what here is. In the left side, the value of R square is 1. That is the highest value it can have. And in that place, the model has no errors. All the data points are lying on that model, on that best fit line. And that is why the error is 0. But if you move to the right, the value of R square decreases and the data points scatter around and the value of error increases. So in the middle of the graph, the value of R square is 0.5, and the model, the data points look a bit scattered, and that's why the value of error has increased. As you move to the right, in the rightmost side, the R square value is 0.05. Here, the R square value is even low, and as a result, you can see the data points are more scattered, more away from the best fit line. That is why a lot of errors are there, and that's why the R squared value is reduced. So that is the significance of an R squared matrix. So if you have built a model and you see that the R squared matrix is in the range of 1 or 0.99, 0.98, or 0.8, then you can have a just in the mind, okay, my model is performing well. But if you have this value like 0.05, 0.01, or 0.1, 0.2, then you can say that, okay, my model is not performing well because the R square value is very low. So a lot of data points are there, which is not agreeing with my model, right? That is what the significance of R squared matrix is. Okay, cool. So this was the cost and stuff. Now we'll talk about some assumptions in linear regression. Like we can't use linear regression every time, right? We need to understand when to use the linear regression model. You see that linear regression, the term says linear. It means that there should be a linear relationship between the dependent and independent variable. If there is not a linear relationship, your linear regression model will not work well. There will be a lot of errors. So if you see that your model is not working linear regression, it might be the case that there is not a linear relationship between your model, between your independent and dependent variable. And that's what we are trying to show here in the graph. So in the left side and in the middle, you will see there is a linear relationship. On the left side, the value of x increases, the value of y also increases. So it's a direct linear relationship between x and y. On the middle of the graph, the value of x increases, the value of y decreases. So there is an inverse linear relationship between x and y. And these two can be very efficiently represented by a best fit line, right? The lines which are drawn here, those are the best fit lines, which can very easily demonstrate your model, right? But on the rightmost side, you'll see that this is not a linear relationship. You'll see that till some point of the x, the rate of which the y is increasing is very steep. But as you move ahead in the x direction, there is a significant increase in the values of y, and that cannot be described by a straight line. If you will draw a straight line and you will go ahead in the x direction, there will be a significant error in your linear regression model, and your model will not perform well. And this is the third case where you should not use a linear regression model, because there is no way to do a best fit line, right? It's made to be a curve which is fitting the entire model. So you can't do a line here. And these are the cases where you should look for maybe that it's better to not use linear regression, maybe go with some other model, right? Second assumption is the normal distribution of residuals. Now, we have discussed the curve, right? The error curve, which we try to minimize, right? There should be a minima so that we can reach there. But there can be some curves where there is no local minimum. And in that case, your Gaussian method will not be able to give you a correct value of P0 and P1. And that's what this thing is trying to tell us that if the error terms or if the error curve is non-normally distributed, then it suggests that some of the data points are not agreeing and you might should not use the linear model, or you should do your data cleanup before using your linear model on that data set. So on the left side, you will see that the error terms are normally distributed, and that's why there is a global maxima or a global minima here. But on the right side, the error terms are not normally distributed. There is a lot of peaks here. There is a lot of minima, a lot of maxima. And at this point, your algorithm will not work. Your Gaussian algorithm will not be able to predict this and come up with a good value. So these are the two assumptions you need to check. So first thing is that whether your dependent and independent variables are in a linear relationship with each other. And the second thing is that there is a normal distribution of the residuals. So residuals was nothing but the errors, that is the difference between the actual and the predicted values, right? Okay. Now, what about, yes, that's what we came here. So Aniket, good question, good timing as well. What about linear regression model? How does that work? So again, linear regression model is a bit difficult to visualize because till now we have one independent variable, and that's why we are able to do y equal to mx plus c. That's a two-dimensional line. But when you introduce one more um, independent variable into it, then your uh, equation becomes y equal to theta 1 x1 plus theta 2 x2 plus c. And that is not two-dimensional, that is actually three-dimensional. And as you put more and more independent variables into your model, the more the dimensions increases. So till three dimensions, I can visualize, but if we go ahead, if we maybe add 4 to 5 independent variables, then it will not be possible to show that in the on a like anywhere on this screen, or maybe like, maybe I cannot show it, demonstrate it physically. So that will work in theory only, but yeah, we'll discuss the multilinear regression model. How does that work? So first thing like to consider while doing a multilinear regression model. So first I'll tell what is multilinear regression. Our multilinear regression model is when you have more than one independent variable. So when you have 2, 3, 4, 5 independent variables, which decides the dependent variable, then that is called a multilinear regression model, right? Now, the first thing is overfitting. So when you have these numbers of variables, there can be a chance that your model can learn each and every deviation or behavior of that data points, and that can lead to overfitting. So overfitting happens when your model learns the training data by heart, so that even if there is a noise in that training data, the model learns that pattern, and that is what is called overfitting. When overfitting happens, you will see a very good training score, maybe closer to 1, maybe 98, 99%. And if that is happening, you should be aware that, okay, this is like better than what expected. And I think that my model has overfit. And in that case, the complexity of model also increases. But if that is the case, if you will go, if you will test that against the test data sets or against those data set that model has not trained upon, your model will perform very poorly. That's called overfitting. We should always watch out for it when you are dealing with multi-regression models. Second is multi-collinearity. So when you are introducing multiple variables into your model, you should not blindly introduce those variables. You should definitely check how those models affect your dependent variables, or how two variables are interrelated to each other, right? And that is called multi-collinearity. If you are introducing two variables into a model and those two models are related to each other, then you should not add both of them, maybe get rid of one of them. So you need to check, you need to understand your data set, and you need to check that if there are two variables which are very dependent on each other, then maybe I will not um, add one of them. Maybe we can strip one of them and we can take another. In that way, your model will also perform well, right? And that's what we talk about in feature selection. So in order to avoid multi-collinearity, you should spend some time doing feature selection or feature engineering. Because when you have a lot of variables, it will not be the case that all variables are good or all variables will have effect on the dependent variable. So if there are some variables which are nonsense or which does not relate to the dependent variable, better to drop them and train your model on a better or a like feature engineer data set or a like filtered data set so that there is a less chance of noises, right? So these are the three things which you should watch out definitely when you are doing multilinear regression. Apart from that, multilinear regression is very similar to the linear regression. And since you are like um, most of the machine learning engineers will not be going into the math stuff. So at the engineering point of view, like if we move away from the maths and research, it does not matter a lot for machine learning engineers. But yeah, these are the three things which you should definitely look out when you are training such kind of models. Okay. Right. So we talked about overfitting, right? We'll try to understand overfitting and underfitting in detail. So overfitting we have already talked about. Overfitting is nothing but when your model tries to learn each and every pattern of your training data set. Like it is learning the training data set by heart and it is trying to mimic all over it. And that is the reason that your training data set might have a very good score. But what happens is that it has actually also like incorporated noise into their pattern, into their model. And that's why when you give a testing data set or some collection of data points which your model has not seen, it will gonna perform very poorly. So in overfitting, what you should look out for is a very high training score and a very low testing score. If that is happening, you should be aware that your model has got overly complex and it is overfitting. Right. Underfitting again is that you have not done proper training or you have not done proper feature engineering. Maybe you have some nonsense features and you have stripped out important features, or you have not trained well. You have maybe you have chosen a very small learning rate or very small epoch value, due to which your model is not able to train or generalize the entire training data set. And that can be the reason that your model is not able to perform in the testing as well. But here, what will happen is that you will not get a very high training score. The training score will also be low, and the testing scores will be eventually very low. So in that case, you should try to fit. So basically, if you have a very low training score, you should be aware that okay, my model has not learned much, and I should spend some time. So you should be like okay, in my training, like if my like very basic model is performing 70 to 80% with a 70 to 80% of the score, then that model can be considered as a decent model. Right? That is what overfitting and underfitting are, and we should be aware of both of these when we are trying to like implement a linear regression model. Okay, now we are at the last topic of this talk, that is degrees of freedom. So what is degrees of freedom? It has not been talked much. So degrees of freedom is nothing but the number of observations that are free to vary when you are doing regression or when you are estimating the statistical parameters. So what is degree of freedom? How you can calculate it? It is very similar, very simple, and minus k minus 1, where n is your sample size and k is the number of independent variables. Now, this is a definition. I'll try to explain you by some graph. So in the left side, you will see we have one independent variable, that is x, and we have drawn a graph here where y is equal to b naught plus b1x plus c, where c or epsilon can be error term which we have introduced. So you can see that with two observations, we will have a zero possibility of error. Why? Because when you plot 2 points on a two-dimensional plane, you can always pass a line through it. And it doesn't matter wherever you put those 2 points, you can always have one line that can pass through those 2 points. And if there is a best fit line that is passing through all of your data set, you will have a zero error. So if you have only two data set, or if you have only two data points and you are being asked to do a linear regression, you should step back saying that I don't have enough data. How doesn't matter however I train my model will perform with 100% accuracy, because I don't have degrees of freedom. I don't have freedom to understand how my data set is performing. So here in that case, you will see the degrees of freedom is zero. That is n is 2, that is the sample size, but the value of k is 1, right? So 2 minus 1 goes to 0. So you cannot have you cannot do a linear regression on with one independent variable having two data sets. So that you cannot do that. You need at least three or more than three data set to do a valid regression, right? So you see that here on, like, since you have one independent variable, you can put that on a two-dimensional plane. And on a two-dimensional plane, you can always pass a line through 2 points. That is the reason there is no error. And that is why you cannot perform a regression on 2 points. But what happens if we introduce more data points? So if we introduced three or four data points, the degrees of freedom increases, right? So now the sample size is three. So 3 minus one, it is one. And the sample size is four, then four minus one, it is two. What is noise actually? I mean, what is underlying? Okay, Akash. So noise is nothing but it is the difference between the predicted value and the actual value. So here you will see that the actual value and the predicted value by the line will coincide, right? So whatever this line is predicting at this point is equal to the actual value, because your line will always pass through that data point, giving the errors or the residual to be zero or noise to be zero. So noise, residual error means the same thing in this talk, right? But when you introduce more and more data set, the errors will increase. So when you have three, you cannot it's not possible to pass a line through 3 points every time, right? It can only be possible when all these 3 points be in line. But if I move 1 point above, like in this situation in the left graph, I cannot pass a straight line from 3 points. And that is why we have one degree of freedom. There is one point which can move freely, giving us some errors, and there where we can have a valid regression. And as we move ahead, we introduce more and more numbers. The more the degree of freedom, the more we have the chances of errors, and we can perform a better regression, right? So that is called degrees of freedom. Now, let's understand with two variables. So someone asked previously, I guess Aniket asked, what about multilinear regression? So that's what multilinear regression looks like when you have two independent variables. So here in this graph, we have two independent variables, that is x1 and x2. And you can understand, like you can easily see that it is not possible to show that in a two-dimensional plane. And that is why this is a three-dimensional plane. That's like what we are living in, right? We have 3 degrees of freedom, like left, right, up, down, right? And in the x-axis, y-axis, and the z-axis, right? So these are the two ways we can move. So this is there are 3 degrees of freedom here. But for this, what happened is that, again, if I say that I have three data points and you have two independent variables, you cannot perform a regression, because no matter what, you can always have a plane pass through 3 points on a three-dimensional surface. If you can imagine, like if you have 2 points, you can pass a line through it. And if it's a third point and you get a third dimension, then you can rotate that plane anyway so that it can pass through that third point. So you can always have a plane that can pass us through 3 points. And that is why the reason is that you will always have a error values of zero, because all those points will coincide on that plane. And that plane will be the best fit plane for that regression, and you will not be able to get any error. Always your model will be performing at 100% efficiency. So that is why, if when the number of variables are increasing, when you are adding more dimensions into your model, you need to provide more data points. So what happens with 4 and 5 data points here? Right. Again, we are in the three dimension. We have two independent variables, but if we add fourth point here, it's not always possible for a plane to pass through all those 4 points. It can pass through 3 points, but fourth point, it's not always possible, because 3 point will restrict that plane at one place. So if that fourth point is by chance occurring at that plane, then it's good. But if it is occurring anywhere from that plane, then it's not possible for the plane to cover all those 4 points. And that's where you get 1 degree of freedom. Now, when you add n equal to 5, you get 2 degrees of freedom. So again, here it is n4 minus k minus 1. That is 4. Since k is the number of independent variable, that's 2. 4 minus 2 minus 1, it's 1. Here, 5 minus 2 minus 1, it's 2. And that's why the degrees of freedoms are 1 and 2, respectively. And that's what you want here. In 3 dimensions or with two independent variable, you should have at least 4 or more observations. Below that, you can't do a regression. So as more you add the number of the independent variables, the degrees of freedom increases. So or basically the number of samples you need to do a regression increases. So suppose I have 5 independent variables, then maybe I need 7 or more observations to do a valid regression. Otherwise, in fifth dimension, I can maybe add something to cover all those 5 points. And that's what maths look like. We cannot visualize more than 3 dimensions, although, but that's what maths looks like. Because if you make a equation, you can have like you can satisfy all those 4 points in an equation, right? But fifth, you cannot. So introducing more variables, more independent variables is very similar to adding more and more dimensions into the model. And I don't want to complicate much, so we'll stick to these 3 dimensions. Rest of if we move ahead with more dimensions, we'll do that maths. We'll not try to visualize that. Otherwise, it can go complex. So that's what degrees of freedom for us. I guess we have 10 minutes left. So what I'll do is that we'll do some hands-on coding. I will try to implement a linear regression model on a very simple advertising dataset, and all of these things we'll do on Kaggle. So I'm gonna share this tab here where we have this model. Okay, I hope this screen is visible. If it's
Yes,
not
yes,
visible,
it is visible.
okay, okay, perfect, perfect. So it's a very small library. I've already tried to uh, go through it. So I'll just walk you through what I have done here. So the first thing is that importing the required libraries. I'll just run it. So what will happen is that all the libraries will be imported, the numpy, the pandas, and the warnings. We don't want the warnings, we are suppressing it. So we are filtering the warnings, we are ignoring them, right? Now what we did in the second step is that we loaded the dataset. So there is an advertising dataset here, which we already have. We have loaded that. So this is the this dataset was present in Kaggle. So within the Kaggle directory, we have pulled this dataset. We have read the CSV, and this dataset looks like this. So if you'll see, there is sales value of the advertisement. So if the advertisement, it is saying that the advertisement was done with TV, radio, and newspaper, and this is how the sales looks like, right?
Can
So
you
for
please
every,
zoom in a little bit? Actually, comments are
yeah,
asking.
yeah, Achha, okay, sure. I think this is good. Or if you want, I can zoom a bit more. Yeah, I can. This is good, right? Okay, awesome, cool. So this is how the dataset looks like. We have newspaper, radio, and TV. There are three ways on which someone is trying to advertise, and they are showing that we did the advertisement through TV, radio, and newspaper, and we did this much advertisement through all these three channels, and this is the sales value which we got. So now what we have to do is that we are trying to build a linear regression model out of it. So first, before moving ahead, we should understand the feature. Like we should understand that whether TV is impacting the sales, is radio impacting the sales, or newspaper impacting the sales, or all of them are impacting the sales. So first, let's do that. So for that, we are doing a scatter plot. So there is a Seaborn library here where we do. So what we did is that we did a scatter plot of sales against TV, newspaper, and radio. And we can see that in this curve. So newspaper is really distorted. It is not making any sense. Newspaper feature is not able to predict this sales value much. But we can see the radio is predicting at some point, but it's very distorted. But if we see at the TV, there is um, a proper pattern which we can see that if the value, if the advertisement through TV channel is increasing, the sales is also increasing. So maybe we can use TV to do a linear regression. So I'm keeping this model very simple. So y is equal to mx plus c, where x is only one feature, and that is the TV feature. And that's what we are trying to do here. So we are taking x as a TV channel. We are taking y as a sales, that is the dependent variable. We have to predict y, right? So we are trying to predict y with x. First we'll do is that we'll try to split this data set into training and testing data sets. 70% to the training and 30% to the testing. And if we do that, if we try to run it, you'll see this. Okay, why it's not defined. Let me see where we went wrong. I guess this should be okay. Yeah, that's good. So again, we'll see that we have this shape of this 140 and 60. The reason is that the entire data set was about of size 200, and if you'll do a 70% of 200, it will be 140, and 30% will be 60. So 140 data items for training, and we are keeping 60 data items for testing our model. That's what we are doing here. We have split the data set. And now what we're trying to do is that we are trying to run it through the ordinary least squares. That is one of the linear regression model, right? So we are building our model here. So all this Gaussian thing will work here, and it will give us a value of constant and TV. And this is nothing but y is equal to mx plus c, where this TV is the slope value, that the feature which is like affecting the TV data set, and constant is nothing but the intercept c value. These are the two values which our linear regression model will return, so that our line will be drawn there. So this is the constant value is 6.9 and this TV value is 0.04. So if this is our model here, so if we see this model, this is the summary, you'll see the R squared matrix here as well, which we described. So R squared matrix is 0.6. So it is a decent metric. It is like not uh, uh, performing very poorly. It's not in the range of 0.05 or 0.12. It is 0.6. So it's not very good, but it is decent. It is okay with this model. The reason is that we have only one feature, because we kept our model very, very simple. And that's what we don't have a very, very good R squared. But this is the one which we can go with, right? Now we have our model ready. Now it's time to test this model, right? So we need to predict that how it is performing on the testing data set. So nothing here. We have our test split with us. We use this model. We predict this test split, and we keep our prediction separate, right? Okay, again, let me check. Okay, this works. Yep. So what it did is that it predicted. We have just mentioned what the prediction looks like. So we have some values of predictions, 7.18 point, the sales value basically against the TV. Now we are trying to understand that how this prediction value is away from the test value, or what is the error between the test and the prediction. And that's what we are trying to do here. So we are trying to compute the RMSE value. For that, we have to give the testing and the prediction value, because it computes the y test minus y pred whole square under root divided by the sample size, right? So if you do that, you will get an RMSE here. So RMSE is 2.8 and R squared is 0.59. So again, R squared is 0.59. So we did this significance slide of R squared, where we see that the higher the value of R squared, the better the model. So here the model, the R squared value is around 60%. So your model is performing with a 60% efficiency. And that's what this uh, analysis is all about. So since we started with only one feature, that is the TV feature, that the TV feature is trying to, that model which we build, a linear regression model, is trying to predict the model is trying to perform with a 60% efficiency. And that's how you build a linear regression. So this is a very simple regression model. You can you should do more feature engineering, and you should try start with a very some complex model with more features, maybe uh, come up with 5 to 6 good features for your dependent variable, and then build a linear regression model out of it. Probably it will give you a decent score, maybe better than this. And yes, I guess that's it. That's what I have for this session. Okay, cool. So yeah, that's what it from my end. Thank you, folks. I hope you like the session, found this informative, right?
Thank you so much, Saurav. There are some questions in the comments if you'd like to address them.
Okay, I guess there is only one question. No, two questions. Sir, I had a question about the previous part. Can we limit the degree of freedom for our data? Is there any normalization? No, you cannot limit the degree of freedom. You see, the degree of freedom is nothing but n minus k minus 1. That is, n is the sample size, which will always be provided by you, right? How many number of samples or number of data items you have. And k is nothing but how much independent variables or how many features you introduce to your data set. So if you're introducing more and more features, you need more and more data set. So if you have 4 to 5 features, so that's the gist here with the degrees of freedom. So if you want a better regression and you have more independent variables, you should make sure that you have lots and lots of data points, right? And degrees of freedom does not affect much to the linear regression model. It's just a minimal point. And most of the times you have a ample of data sets. You have at least you will have 1,000 data points in your data set. And if you are going with like 500 uh, independent variable, then definitely it's not a good model. You should keep your independent features around 10 to 15 after doing some proper feature engineering, and that would be the sweet spot. So maybe 10 to 15 good features with a data set of maybe 500 or 1,000. That would be good to go with. But this is a very small data set, 500,000. You'll probably have like thousands and lakhs in a decent data set. So you should not worry about degrees of freedom. It will be okay. You don't have to minimize or limit the degree of freedom. There is no point of actually minimizing the degree of freedom. Won't achieve much. Okay, another question by Rashmi. As you said, global minima is reached and it depends upon learning rate. How do we calculate the particular learning rate for our models? So again, you cannot calculate, there is not a given straightforward calculation for a learning rate. It totally depends upon your uh, curve, that is the error curve, and it depends upon your data points. So you will always have to experiment with your learning rate. Give them a value, maybe 0.1, 0.2, and see how well your model is performing. You will understand that when you will give a very small learning rate, you'll see that your model is taking a lot of time to perform the computation. And if you're giving a higher learning rate, you will see that your model is not able to perform well. And that's where you understand that, okay, maybe I have to give increase the learning rate, or maybe I have to decrease the learning rate. So that's what you do. You probably experiment with those epochs and learning rate values to come up with a good value, good decent value for your model. Yeah.
Thank you so much for the session. I have dropped the LinkedIn of Saurav in the comments and also a feedback form if you'd like to fill that. So thank you so much, Saurav, for joining us for your insightful session. In my opinion, it was a really great session. The linear regression is a topic that is like quite good to understand, and you made it really helpful. So thank you so much guys for joining. We'll be back tomorrow with our day 7. Keep following our socials. The link to the socials will be in the description. Also this stream will be saved on YouTube, so you can share it with your peers. Thank you so much for joining.
Thank you, everyone.